Okay, we're back to talk and finish up our discussion on free fall. Last time we defined free fall as being a state of motion in which gravity is the only influence on an object's motion. So when we talk about free fall, we just have to realize, is gravity the only thing that is causing the object's motion to change? If that's true, the object is in free fall. If not, it's not. We talked about how objects that are in free fall accelerate at a certain rate, 9.81 meters per second squared, toward the ground. And we even looked at an example of an object falling from rest toward the ground, where the acceleration stayed the same, but the velocity continued to get bigger and bigger, directed towards the ground. We're going to look at another situation now, in which we have an object that is getting launched straight up and then falling back towards the ground. So below is a picture representing the position at different points in time of an object that has been launched straight up in the air. It's not going exactly straight up so that we can track the motion both going up and down. For the first point in time, the velocity and acceleration vectors have been added. Draw the velocity and acceleration vectors for the rest of the points. Well, we know that the acceleration, if this object is in free fall, which it is the entire time, okay, it's just after launch right here, and all the way around, it's always only being affected by gravity. Nothing else is touching it. Even right here, this is right before it hits the ground again, it's still in free fall. We know that objects have constant constant acceleration when in free fall. The acceleration is 9.81 meters per second squared, and it's directed toward the ground. So all of these points have the exact same acceleration. So I'm going to label that. All the acceleration vectors should be approximately the same in length, and they should all be pointing towards the ground to show that the acceleration has not changed. Now the velocity vectors, on the other hand, are a different story. Initially, the velocity is very big and it's directed upward, but common sense tells us that's not going to remain the case. We know that objects slow down as they reach a peak and then they fall back towards the Earth. So the velocity at this point, the velocity is just the direction that it's moving. At this point, the velocity is positive, or I shouldn't say positive, but it's directed upward. At the peak, there is no velocity, and then as it comes back down, the velocity is downward. That's the direction it's moving at that point. How would the velocity vectors look? Well, think about it like this. Since the velocity and acceleration are in opposite directions, as we talked about a few videos ago, that must mean the object is slowing down. The velocity, the upward velocity, shouldn't be as big at this second point. Gravity has slowed it down so the object is not moving quite as fast. By the time it rises up to here, now it's moving even less fast. So we have an even smaller velocity. At the peak, there is no upward velocity. This is the highest point that it's reached. It's not yet falling back down, but it's also not going up anymore. So the velocity is neither up nor down. There must be no velocity. And then the object starts to fall back down. At the point where there's no velocity and the acceleration is still directed downward, that's going to make a downward velocity start to emerge. The neat thing is, because these objects are drawn at the same height, the size or magnitude of the velocity here and here is going to be the same, but it's going to be in different directions. That's a neat little trick that you can use. If an object is at the same height when it's going up as it was when it was, or as it goes down as it was when it was going up, the magnitude of the velocity, the size of these velocity vectors is the same, but their direction is opposite. Here the ball is still moving up, here the ball is moving down, or the object, whatever it is. Now notice that the velocity and acceleration are in the same direction, so that means the object must speed up. The velocity will increase in the downward direction. And then finally, when it gets to the ground, right before it gets to the ground, the velocity is again the same as it was when it got launched, but it's pointing in the opposite direction. Okay, so that's how the vectors would change as we go through this object's motion when it's in free fall. The acceleration is always the same. The velocity decreases to 0 at the peak and then increases but in the opposite direction. So let's answer some basic questions about this. Number 1, when is this object in free fall? Is it in free fall before it's launched? No, it's probably still in contact with the ground at that point, or the person launching it. What about as it's going up? Yes, even though it's not falling, the only influence on it at that moment is gravity. it doesn't matter that it was launched beforehand. It's not still in contact with whatever is launching it. So therefore, the only influence on it currently is gravity. It must be in free fall. At the top of its flight, same answer. It's still in free fall because it's still only being influenced by gravity. On the way back down, also in free fall. But once it's landed, once it starts, even just barely starts to make contact with the ground, no, it is no longer in free fall. Describe what happens to the acceleration. Look at those acceleration vectors. There's no change. It is constant. Describe what happens to the velocity. This one will take some work. I'll say initially, upward, decreases to 0 at peak, then increases in opposite direction, which is downward, on the way back down. We kind of already answered this one, but what is the velocity at the object's highest point? What is the velocity at the highest point in the object's motion? Well, at the highest point, it's no longer moving up, but it hasn't started moving down yet either. That means the velocity must be 0. So I'm going to write in 0 meters per second. We've also talked about this one. What do you notice about the velocities just after the object is launched and just before it lands? We've talked about how in free fall, an object, if it gets launched straight up and comes back down, it passes each height twice, once on the way up, once on the way down. The velocities at those heights have opposite directions, but the size, the magnitude of the velocity is the same. So I'm going to write this. And you'll hear this phrase a bunch during this course. The velocities at the point just after it's launched and just before it lands are equal in magnitude but opposite in direction. The next question is, does the velocity of the object change at a constant rate? And the answer to that is actually yes. That's what acceleration tells us. The acceleration is constant, and the acceleration is the change in velocity over a period of time. Another way to think of that is the change in velocity for, let's say, every second. 9.81 meters per second squared means that the velocity changes by 9.81 meters per second for every second that the object travels. So if these are seconds, okay, if this is 0, this is 1, 2, 3, then that means that the object went from some speed here to or some velocity here to a velocity at this point that is 9.81 meters per second less, and 9.81 meters per second less here as well, and then 9.81 meters per second even fewer here. Once it gets to the peak, the velocity starts to grow because now the velocity is pointing in the same direction as the acceleration. So from here to here, we have an increase of 9.81 meters per second. Here to here, 9.81 meters per second. Here to here, 9.81 meters per second, as long as all these dots, if these dots were separated by 1 second each. That is how acceleration works. It tells you how much the velocity changes each second. So does the velocity of the object change at a constant rate? Absolutely. It changes at a rate of 9.81 meters per second every second. Does the distance from the ground change at a constant rate? Let's apply the same thinking. If this is 0 seconds and this is 1 seconds, does the distance change the same from 0 to 1 as it does from 1 to 2? Very clearly not. Does it change the same from 2 to 3? No. And that has to do with the fact that it's only the velocity that is changing at a constant rate. Okay? If the velocity is changing all the time through here you're moving at a speed much greater than you were here. So automatically you're going to travel farther from here to here than you were from here to here, because at this point you're traveling at the slowest pace that you were during this first second. So no, the distance does not change at a constant rate. Last question. How do you think the times compare? How does the time that the object takes to go up to its maximum height compare to the time that it takes to go back down from its maximum height? In other words, the time from here to here, and the time from here to here, what do you think is greater? We can prove this in class, but you'll see that in this case, they are equal. Objects take the exact same amount of time to rise up to their peak from the ground, from their launch, as they do to fall back down, providing that the object is launched and lands at the same height. Okay? The time from launch to peak is the same as the time from peak to landing. So, let's sum up and take a very quick look at a very brief example. Let's sum up everything we've done with free fall so far. For an object that gets launched straight up, I like to say that the motion is symmetric. This is one we just talked about. In other words, the object takes the same amount of time going up as it does coming back down. The main reason for this is that the acceleration due to gravity is constant. It does not change for an object in free fall. Matter of fact, it doesn't change while the object is in free fall. It doesn't change while it's going up at the peak or coming back down. It also doesn't change from object to object. Every object accelerates, if every object in free fall accelerates at the same rate. The acceleration due to gravity, 9.81 meters per second squared towards the ground. Make sure you're not getting velocity and acceleration confused. The object can be moving up if it's in free fall, but the acceleration for an object in free fall always points straight down. The acceleration due to gravity is constant. It is always present, even at the top of the motion when the velocity of the object is zero. Just because you have zero velocity does not mean you have zero acceleration. The object still has an acceleration at the peak. It is still 9.81 meters per second downward. However, the velocity is zero. The object passes each height twice, once on the way up and once on the way down. If you are comparing the velocities at the same height on the way up and on the way down, it is apparent that the velocities are equal in magnitude, but opposite in direction. In other words, we did the example right when the object was launched to right when it landed, the velocities had equal magnitudes. So if it was launched at, let's say, 30 meters per second upward, it's going, right before it hits the ground, it's also going to have that speed, or that velocity, the magnitude of the velocity will be 30 meters per second. It will just be directed downward as opposed to upward. And then the last point that's important to remember about free fall, at the very top of the object's motion, for one instant in time, the velocity is neither up nor down. The velocity is instead zero. And that's a really important point to remember because it can help us with problem solving. Let's look at this example to solidify these understandings. A model rocket is launched straight up with a velocity of 30 meters per second. Now, that doesn't mean the velocity is always 30 meters per second. We know that once it's launched, this model rocket will be in free fall. But that's the velocity that it starts with. That must be the initial velocity. So the initial velocity I'm going to write down is positive 30 meters per second. What is its maximum height? We want to know the height. That's the distance. That's d. Now you might say, well, hold on, that's the only things we know. How can we do this? If you think about it, you can figure out at least two more things that you do know. Since we're looking for the maximum height, that's the height of the peak when the rocket stops moving upward but hasn't started moving downward yet. We just got done talking about how the velocity at that point is zero. I know that's not the final point in its motion, but final velocity in this case, if we're looking for the maximum height, would be 0 meters per second. Final velocity doesn't refer to the absolute final. It just means some velocity after the initial that you are concerned with. Okay? So in this case, since we're trying to look for the distance or the height that the rocket reaches at the very peak, we're going to say the final velocity is 0. We also know, since this object is in free fall, that the acceleration of the object is 9.81 meters per second downward. Now that's going to be a little tricky because the initial velocity we said was 30 meters per second, and that's upward. If we're dealing with vectors and we said that the upward vector is positive and we have another vector that's downward, that vector needs to be negative. And from now on, you're going to have to figure out, before you even start a problem, what direction you want to be positive. So before you do anything else, before you even list out your table of variables, you always want to define a positive direction. In this case, it was done for us, okay? It told us that the rocket was launched up with a velocity of positive 30. So that means that up is positive. The only thing that that does for us is that means that anytime we have a vector that is upwards, it has to be positive. Anytime we have a vector that's directed downwards, it has to be negative. So our acceleration must be negative in this case. If you think about it, that makes sense because since we have a positive velocity and a negative acceleration, the object must be slowing down, and we know it has to slow down to 0 meters per second at the top. The only other variable that we haven't talked about yet is time, but they don't even mention time for us. As a matter of fact, we're going to find the time later on. So we now look at what we know. We know the initial velocity, we know the final velocity, we know the acceleration, we don't know the distance or time. Right now we're looking for the maximum height, which is a distance. So I'm going to go to my reference tables and I'm going to look to see what equation might help us here. I know the first 5 right now. I've talked about all of those. We need one that has initial and final velocity, acceleration, and distance so that we can solve for it. So that means anything with time is out. Out, 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 out. The 5th equation seems to be the useful one here. Vf squared equals Vi squared plus 2AD. Since the final velocity is 0, I'm going to put the arrow with a 0 over it, so I know that cancels out. The initial velocity is 30 meters per second squared plus 2 times the acceleration of negative 9.81 meters per second squared multiplied by d. 30 squared is 900. 2 times 9.81 negative is negative 19.62 d. Now I just bring one of these to the other side and divide by 19.62 to find the distance. Turns out that the maximum height of this model rocket is 45.87 meters. Now, another thing that I just thought of, some people might say, well, the initial velocity wasn't really 30, wasn't it 0 because it was at rest on the ground? That's true, but we only care about while this object is in free fall. Okay, I know the velocity was 0 when it was sitting on the ground, but this specifically tells us that at launch, when it just leaves contact with the ground, the velocity is 30 meters per second. As soon as that happens, as soon as it's in free fall, it starts accelerating back towards the ground. That doesn't mean it immediately moves back towards the ground. That just means the velocity will start to change from 30 meters per second at the rate of 9.81 meters per second squared towards the ground. So our kinematics equation tells us that the maximum height is 45.87 meters. What is the total time that the rocket was in the air? Well, now that we know the distance, we have a couple different ways we could find the time. I think the easiest, since we already knew the final velocity, the initial velocity, and the acceleration, is to use the Fiat equation. Vf equals Vi plus AT. My final velocity I know was 0 at the top, so I'm going to write 0, and I'm going to come back to that in a little bit. The initial velocity was 30 meters per second plus the acceleration, negative 9.81 meters per second squared times t. I bring one of them to the other side, and then I divide. 30 divided by 9.81 gives me a time of 3.06 seconds. But that's not my answer. Think about this. That's just the time for the velocity to go from 30 meters per second upward to 0. It's 0 at the peak. I need the total time that the rocket's in the air. So I can do this. Since I know it takes the same amount of time for the rocket to go up as well as come back down, I can take that time and multiply it by 2, and I get the actual total time of 6.12 seconds. That's the total time. Now, some people might say, I don't want to remember to do that. I want to actually, and actually I'll come back to that. Okay, some people might say, I don't want to remember to do that. There is another way to do this problem. But first, let's do this. What is the final velocity of the rocket just before it hits the ground? Now, this could be a little tricky as well. We do know a trick for doing this, but I'm going to show you why that trick is useful. The final velocity when it hits the ground, I know the final velocity at the top. Why don't I do this? Why don't I write out my variables that I know at the top? At the top, My final velocity initially from the ground to the way up will now become my initial velocity. If we start from the top, the initial velocity is now 0 meters per second squared. I'll keep the acceleration as negative 9.81 meters per second squared. This indicates that up is still positive because the acceleration points down, and I'm saying that that's a negative number. I know that it will take the exact same amount of time to fall back down, 3.06 seconds, and I'm looking for the final velocity. I use the Fiat equation again. Initial velocity is 0. Final velocity, acceleration is 9.81 meters per second squared, multiplied by 3.06 seconds. And I get, with a little bit of rounding, because I did round that 3.06 seconds up here, I get approximately negative 30 meters per second is the final velocity, which just goes to prove what we were saying before. Whatever the launch speed is, as long as it lands at the same height, the landing speed will be the landing velocity will be the same, at least the magnitude will be the same, the direction will be different. Okay? So this shows us equal in magnitude to launch velocity, but opposite in direction. Now, what if, let's go back to that second question. What if you didn't want to have to remember to multiply by 2? Another option is to do this. You still use the Fiat equation. Remember, we're solving for the time that the rocket's in the air. You write down that the initial velocity is positive 30 meters per second, but notice that we just found that the final velocity at the total end of the rocket launch is negative 30 meters per second right before it hits the ground. If I plug in negative 30 meters per second here, so I go from launch speed to, or launch velocity to landing velocity, and I still plug in the negative 9.81 meters per second squared, watch what happens when I solve for the time. I would have to subtract 30 over to the other side. Negative 30 minus 30 is negative 60. Then I divide by negative 9.81. And I get t is equal to 6.12 seconds. So you have options, okay? You can either solve for the time, if you're looking for the time for something that gets launched up and comes back down to the same height, you can solve for the time just one way, just going up or just coming down and then double it, or you can think of it like this. Take the launch speed and the launch velocity and the landing velocity, make sure you have the correct signs assigned to each, and plug them into the Fiat equation. That will work as well. All right, so we've covered free fall. We've looked at a couple different situations involving free fall. Free fall questions are usually fairly prevalent. What we're going to do in the next set of videos is get ready to start talking about projectile motion, in which, or what I should call it is two-dimensional motion, in which we have an object that not only moves up or down, but possibly moves side to side as well. So far we've only done one-dimensional motion. Now we're going to start looking at two-dimensional motion. Okay? It's a little bit of a step up in difficulty, but you guys have done well with free fall and one-dimensional kinematics so far, so it's time to do two-dimensional. I'll see you later.